Okay, folks, I'm going to do problem 5.11b. Chapter 5 is on root locus, and this is a, let's see, 1, 2, 3, 4. This is a fourth order system. You have your reference input, R, your error signal, it's just proportional control, your transfer function, s plus 2 in the numerator, s minus 2, and then s squared plus 2s plus 10. S squared plus 2s plus 10. All right. And then the feedback signal, obviously. This is your input, this is your output. And so obviously this system is unstable. There's a positive pole here, s plus 2. I'm going to go ahead and write the... Actually, we need to close the loop first. I don't know what I want to do first. So here's the thing. Part A is do a route table, okay, to find a range of K. Okay, and then part B is to create a root locus. Okay, so I'm trying to think if I want to do both, if I want to close the loop or not. I think I'm going to go ahead and close the loop because if you want to do a route table, you need to close the loop. But keep in mind, I don't want to erase this because that's going to kind of mess things up. All right, so in order to close the loop, you're going to get let's just throw this marker away. You're going to get K, s plus 2 over s minus 2, s squared plus 2s plus 10, all over 1 plus k, s plus 2, s minus 2, s squared plus 2s plus 10. And again, this is C, this is G, H is equal to 1, and your closed loop is CG over 1 plus CGH. That's the closed loop formula. This is improper, so you're going to multiply by the denominator, so you're going to multiply by s minus 2, s squared plus 2s plus 10, over s minus 2, s squared plus 2s plus 10. Okay? This is going to cancel with that, that's going to cancel with this, but this is also going to multiply over there. So you're going to get ks plus 2 in the numerator, and you're going to get, I'm going to multiply this through, you're going to get s squared minus 2s, s squared plus 2s plus 10, plus, I'm going to multiply that through, you're going to get plus ks plus 2k. Okay? In order to do the route table, you're going to multiply this out. So you're going to get a s to the fourth. That's going to take care of those two guys. This is going to give you a 2s cubed, but this is going to give you a negative 2s cubed, which means those terms are going to cancel. And then you're going to get, so there are no s cubed terms. I'm going to get 0s cubed. And then you're going to get a 10s squared and a negative 4s squared, so you're going to get plus 6s squared. And then you're going to get a negative 20s plus ks, so you're going to get k minus 20s, and then plus 2k. Okay? So there is your polynomial there. I'm going to rewrite it up here. So s to the fourth, 0s cubed, 6s squared, k minus 20s, 2k. Okay? Let's go over my 3D printer here. Alright, and then I'm going to erase this down here. Okay? And then I'm going to draw an arrow so when I take a picture I'll still have it. Okay, so let's build the route table now. So you're going to get s to the fourth, and the first row is going to be 1, 6, 2k. The second row is going to be 0, k minus 20, 0. And then you're going to get s squared is going to be h. This is going to be... Is this actually going to give you something? This might actually give you something. I guess I'll call this P. This is definitely going to give you 0. and then s to the first, you're going to get q. So I need to compute those three determinants. Now, if you notice, this term here, this 0 is going to give you problems when you start doing the derivation. So you need to just replace this with epsilon, at least that's what they do in the book, and then just proceed. For now, just leave epsilon as a variable, we'll deal with it at the end. Okay, so h is minus determinant over epsilon of 1 epsilon and then 6 k minus 20, okay? And so that's going to give you, I saw somebody do this the other day, like instead of doing this minus that and then putting the negative sign, just do this minus that. So it's 6 epsilon minus k minus 20 over epsilon, okay, and that's h. And then I guess I should reduce this. This is going to give me 6 minus k over epsilon plus 20. Yeah, minus k over epsilon plus 20 over epsilon. Yeah, I don't really like that. I'm going to leave it as, I'm going to do plus 20 minus k over epsilon. And that's h. I call that h there. Okay? How's that? Let's see. Let's do p. So p is minus determinant of 1 over 1 epsilon, and then up and to the right gives you 2k 0. And then, let's see. Is that right? Up and to the right? Yeah, okay. So then that's going to be, again, I'm going to do it backwards. I'm going to do 2k epsilon minus 1, 0 all over epsilon. So that just gives me 2k, so that's p. So I'm going to go ahead and just, well, no, that's fine, I'll just leave it. Okay, so there's p. P is this 2k. Alright, and then now we just need to compute q, and then we're done. So q, well, we're done with the table, we still have to analyze it afterwards, right? So q is minus determinant over h, and then you're going to get epsilon h up and to the right is going to give you k minus 20. I gotta watch my posture here. And then p. Ooh, this is getting nasty. So again, you're going to get, let's see, k minus 20 h minus epsilon p all over h. And then the h's will cancel, and so you'll get q is k minus 20 minus epsilon p over h. Okay? Alright, and then what you do is, should have grabbed my stool. Okay. What you do is you write the first column. So the first column is 1 epsilon h, which is 6 plus 20 minus k over epsilon, and then q, which is k minus 20 minus epsilon p. Oh, and p is 2k, we already knew that. Epsilon 2k over h. I wonder if we should substitute in h, because won't an epsilon cancel? Whatever. Alright, 1 is greater than 0. Epsilon is greater than 0. So I was going to say before, like, we'll deal with this later. So what you need to do is you need to determine the bounds as epsilon goes to 0. Okay? So if epsilon is greater than 0, that's fine. It's going to approach the limit from the right. So it's like going from infinity down to 0 from the right. And so this term here has to be greater than 0. So you're going to get 20 minus k over epsilon has to be greater than negative 6. And if you multiply by epsilon, which is still positive, you're going to get 20 minus k needs to be greater than negative 6 epsilon. And then you're going to add k to this side, so you're going to get 20 plus 6 epsilon has to be greater than k. So basically, if epsilon is approaching 0, it basically means that k has to be less than 20. That's what that says there, okay? So then now let's do q here. So q, I guess I'm gonna crouch because I forgot to get my stool. So k is, so then down here you're gonna get k minus 20 minus epsilon 2k over h. And you're going to get, that needs to be greater than 0. You're going to factor out, you're going to combine like terms, so you're going to get k times 1 minus 2 epsilon over h. Oh, but h, see that's what I'm saying, h has a k in it. You've got to factor this in. I'm running out of board space here. I'm going to take a picture of this and then come back. Where's my cell phone? There it is. I don't like to solve these problems while I am before I shoot the video, because I like you to see my thought process when I'm walking through this. And so sometimes it makes for a longer video, but hey. Hopefully this helps you learn a little bit more. So let's go through this one more time. Let's make sure I'm right. So you get, let's see, s plus 2. Let's make sure I wrote the problem down right. S plus 2, s minus 2, s squared plus 2s plus 10. So ks plus 2 over s minus 2, s squared plus 2s plus 10. You multiply top and bottom, and so you distribute, so you get s squared minus 2s, s squared plus 2s plus 10, plus ks plus 2k, so that's here. And then you're going to get an s to the fourth term. You're going to get a 2s to the cubed minus 2s to the cubed, so those cancel and you get a 0s to the cubed. Then you're going to get a 10s squared minus a 4s squared, so you get a 6s squared. And then you get a negative 20s plus a ks, so you get k minus 20, and then you just get a 2k. Okay. Alright, so then you get your polynomial, you write out your coefficients, 1, 6, skip 1, 2k, and then you get 0, which turns into epsilon, k minus 20, and then 0. You get an h here, so you do minus determinant of the first column, and then up and to the right gives you 6k minus 20. And so you get 6e minus k minus 20e. The e's cancel here, and so you just get 6 plus 20 minus k epsilon. And we solved that down here for 6 plus 20 minus k over epsilon greater than 0. So you get, see, I hesitate, see this is the only issue, I hesitate to like multiply by epsilon, you know what I mean? Like if epsilon is approaching infinity, oh I see. If epsilon is approaching 0, this whole term is going to approach infinity. So this term, oh okay, I see, this term is going to dwarf that term. That's why this goes away. And so since this term dwarfs that term, you basically just need this numerator to be greater than 0. Okay, that makes sense. Okay, so let's look at Q. So I already have this board here, so I already have this here. K is less than 20, so I'm going to write that over here. K is less than 20, okay? And then I'm going to rewrite Q. Oh shoot, I erased H. I need H. H is right here. So H is 6 plus 20 minus K over epsilon, okay? And then P I think was 2K, which is here, because I forgot I needed that. And then Q is K minus 20 minus epsilon P over H. Okay, so what we need to do is Q needs to be greater than 0. But we need to substitute in those variables. So you're going to get Q is K minus 20 minus epsilon times P, which is 2K, over H, which is 6 plus 20 minus k over epsilon, okay? And that needs to be greater than 0. Find the range of k. Okay, so I'm going to do a couple weird things here. So I know that I'm going to bring this to the other side. So I'm going to get k minus 20 minus epsilon 2k. Sorry, it needs to be greater than epsilon 2k over 6 plus 20 minus k over epsilon. And then I'm going to multiply by epsilon over epsilon. Is that okay? That's fine. So I'm going to multiply by epsilon over epsilon, and that's going to give me k minus 20 has to be greater than 2k epsilon squared over 6 epsilon plus 20 minus k. And I'm going to go ahead and multiply this to the other side. And I know, I don't need to flip the sign because I know this is always greater than 0 because I know h is always greater than 0. So if I do 6 epsilon plus 20 minus k times k minus 20 has to be greater than 2k epsilon squared. Now I need to distribute this or factor that, so I'm going to get a 6 epsilon k. I think at this point actually, I think I can go ahead and plug in epsilon 0. Because see before, yeah, I think it actually would be fine if I did this. If I did epsilon was so I'm going to get 20 minus k, and k minus 20 has to be greater than 0. And I think it's easy to see that this is always negative. So the only way that this is strictly negative, yeah, I mean this is, like, no matter what, I mean you're going to get negative k minus 20 squared. And there's no way to make this greater than 0. Unless k was equal to 20. And then you would have 0 is greater than 0, which is still not true. So is this never stable? Okay, so I spent a lot of time on this video, so I'm going to assume this is never stable. And I'm hoping this is like a trick question, or I guess I'll review the footage and see if I missed something. I might have to do this problem by hand. But I'm going to say it's never stable. I'm going to take a picture of this, and then I'm going to do a root locus, and let's see what we get. So every now and then I'll do a problem that I don't know how to do, and I figure it out, and then like I said, every now and then I'll do a problem and I don't know how to do it. I have to go ahead and do it by hand. So this might be one of those problems. But no big deal. So let's do a root locus now. Okay? So a root locus will be, I think, a lot more straightforward. Okay, and so in this case, this is pretty simple. This is g, and I need 1 plus kg equals 0. And so basically I have zeros at -2, and then I have poles at 0, positive 2, and then whatever this is that factorable? 5 and 2? No. So it's going to be -1 plus or minus 1/2. B squared is 4 minus 4ac, that's minus 40. So that's -1 plus or minus 1/2 square root of -36. So that's -1 plus or minus, is that 6i? Yeah, so it's 3i. Okay, so then we have -1 plus or minus 3i. Okay, so we can make our Routh table now, or sorry, our root locus, I'm sorry. So you've got a positive pole here at 2, you've got a pole here at 0, you have a pole at -1 plus or minus 3i. Here and here. It's easy to see that when k is 0, your open loop poles are unstable. You have a 0 here at -2, okay? So one of these poles is going to go this way. Okay, so now let's do our, let's turn the crank here. So n minus m, which tells you the number of asymptotes. The number of poles is 1, 2, 3, 4. So n is 4. The number of zeros is 1. So there are 3 asymptotes, which makes sense. One of these poles is going to go to that. If I had to guess, these two are going to come together, split, come around, combine, and then come this way. If I had to guess. It's possible this could go out to positive. No, that's not possible because that's an even number. So yeah, I think these are going to combine, split, come around this way. The question is do these go to positive infinity or negative infinity? If they go to positive infinity, then this system's probably, like I said, always stable. If it's negative infinity, then actually it's possible to stabilize this system. And then my root locus is wrong, and I guess I'll have to go back and check. Okay, so, oh, and m was 1. Okay, so then my alpha, which is where my asymptotes intersect the real axis, is the sum of the poles minus the sum of the zeros all over n minus m. So the sum of the poles is 0 plus 2 plus, and here's the thing, the 3i is going to cancel, so I'm just going to do -1, -1. And then minus the zeros at -2, all over 3. So this is going to be 2 minus 2 plus 2, so this is positive 2/3. So right here, at positive 2/3, my asymptotes are going to come together, okay? Alright, so I'm hoping that my asymptote shoots that way. If it shoots this way, then that means the system is always unstable, unfortunately, okay? So let's see, phi L is 180 plus 360 L minus 1 all over n minus m. So in this case, phi L is 180 over 3 plus 360 over 3 L minus 1. 180 over 3 is 60, 120, 180. Then 360 over 3 is 120, L minus 1. And so that means phi 1 is 60, phi 2 is 180, and then phi 3 is 320, 300. Okay, so that means I've got an asymptote this way at positive 60, an asymptote this way, and then I've got an asymptote that way. Okay, so it's unclear. It's actually unclear to me now which pole goes where. So now we need to do the real axis test. So the real axis test says, look over here, how many poles and zeros are to the right? There are 0. That's an even number, which means nothing on this part of the axis is on the real axis. If I go here, now I have an odd number, which means this whole section is part of the root locus, okay? So I was right, these two come together and meet. The problem is that there are these two asymptotes here, which means that unfortunately these meet and shoot this way. So again, this system is always stable. So my root locus, my Routh-Hurwitz was correct, it's always stable. So this is honestly kind of a BS question. It says find a range of k for which k is stable, and I honestly, I feel like that was kind of a trick question. That's not really fair, because it's always unstable. Anyway, if we go here, there are 2 poles to the right, that's even, so everything from here over is not part of it. If I go past this complex conjugate, that's 1, 2, 3, 4, that's also even, which means this is not part of it. But if I go here, I've got 1, 2, 3, 4, 5, which means everything over here is part of the real axis. But if you notice, there's no poles over there. So where do these go? Well, these two are already going towards these asymptotes, which means one of these poles needs to go towards the asymptote. So that means one of these poles needs to come down and go that way. And so where does this pole go? Well, complex conjugates move in pairs, so it means that this one has to come in and meet. And again, you only have 3 asymptotes, which means that one pole is going to go to the 1, 0, right? There's only 1, 0. And so that means this one has to come this way. Okay? And so there's your root locus. And so honestly, that route table is kind of garbage if you ask me. This route table, or this root locus, was way easier to create, and it's extremely easy to see that it's always unstable, right? These poles are always going to be in the right half plane. If you had to ask me, I would think you would need some sort of lead lag compensation to stabilize this. Proportional control is just not enough. I would say it's because of this integrator here. If you didn't have this integrator here, I think things would be a lot better, because then you would have, right over here would still be odd, and so I think this pole would go that way. That's my guess. So I think you need a lead lag compensator on this one. Anyway, sorry about the book giving you a trick question. Hopefully this helps. If you have questions about the route table or the root locus, again, I like the root locus way better. But if you have questions about it, just post in the comments, and hope you have a nice day.